Okay, so let's start the introductory part. Um, okay, so I'm assuming most people have uh, all these data and software already. And I do really recommend you open up imagingscoretutorial.py on the GitHub page or download it so that you can copy and paste, do copy and paste. So it'll be much more efficient. See something in the chat. Working with CASA for the first time, can you walk through it? Yes, I am going to, but yes, before that, I'm still going to walk through some, so this is just some quick recap from the lecture this morning. So, like we know that using interferometer arrays, we are discretely sampling the UV space. And so remember, short baselines are measuring the extended emission and long baseline are measuring the small scale emission. And even with like ELMA, with huge number of antennas, we still have the problem of missing short spacing because of the limit of distance between two antennas. And so that's why we also have to combine data with total power. So yeah, this is just another example showing missing short spacing. So like if we have two sky models, one with a diffuse component and one without, and we observe it, theoretically, if we observe with a full range of spatial scale, you will see that different. But if we cut a central hole and only include the long baseline, they are basically indistinguishable now. So, so the large scale emission is undetectable with long baselines. And so we should always keep in mind that there are limitations of angular scales that our data can recover. So basically, the point is, the reason why we need to clean our image is because there are gaps in the UV coverage. So here you are seeing a dirty image and a cleaned image of the TW hydrate. So you could imagine like if we simply grid the measured visibilities and then throw them into Fourier transform, we would get a dirty image like this with many artifacts, like these bright blobs that we know they should not come from the real signal. And by cleaning, you can see that these artifacts are now much mitigated. So that's why we need to clean up for those, use clean to clean up for those artifacts. So here is a detailed step-by-step procedure of what clean is doing. So clean is basically the deconvolution algorithm we use to cut down those artifact structures. So before I step into this procedure, I just want to say all these steps are covered by one single CASA command called tclean. So don't worry too much about it if you don't fully get into each of these steps. But what's happening behind the CASA tclean is at first it would construct the observed dirty image and the dirty beam or point spread function by Fourier transforming the UV coverage to get dirty beam and Fourier transforming the raw calibrated visibilities. And then tclean search for the location of peak and amplitude in these dirty image. So we're basically assuming that the first few identified peaks are coming from real signals. And once we identify a peak, we add a delta function of this peak at that location to our model. So you can see some peaks in our model. And then we convolve the model with the dirty beam and extract those from our dirty image. And we do this iteratively until some stopping criterion is reached. And usually that is when we think the residual of the real signal match the level of the noise. And so to restore the final cleaned image, we smooth the model with a clean beam and add in the final residuals. So as I mentioned, this is all taken care of with T-clean. So the only thing we should worry about is when should we stop? Yeah, so the only thing we should do is to set a stopping criteria in the T-clean command. Okay, so first of all, let's start running some simple command in CASA. So before we actually create an image, we of course want to know a little bit more about the data set. So now you can try to open CASA. So in this case, I can demonstrate here. So I'm running on a remote machine. So if you have the script ready, you can copy and paste the first line, the list ops. Oh, preferably the all-in-one command. And you could, I could bring up CASA, and then so there will be an interactive thing popping out. And what I need to do is, oh no, I cannot see the GitHub page right now. Copy and paste the list ops here to the and yeah, so this basically lists the observational setting, like each observational scan, what is the field ID number and what is it. So in our case, the science target is T over hybrid. So some basic information. And it is actually also very handy if you put in list file. So you could print all these information into a file. So just do list file equal, let's say, list ops documents. And then, okay. It's a bit laggy. Yeah. And so then if you go back to your directory, if you go back to your directory, you will find the text file with all the information. So so try this and let me know if you have questions running the list ops command. So what I did was this command with list file.
When you were SH to elevated, no, when you started CASA, it said I could not create the logger. You know why? When you started CASA.
When I started CASA, oh, it's because right now I'm not using VMC, so it doesn't have a display for that. Yeah. I see some message from chat. So everyone good for this step? Okay, awesome. So the next step is we can start inspecting our data using plot.ms. So basically, this is just a command to create plots. For example, we definitely want to check the UV coverage. So with plot.ms, we set x-axis equal U, y-axis equal V, and the others are just like if you want to average channels and average the spectral window, and there should be a figure like this popping up. So try it if you haven't, and I'm also going to try it just to make sure I don't underestimate the time that is needed. So just a real-time demonstration. If I put plot ms, like copy and paste the command and press enter, it would pop up a screen with UV coverage. This. So yeah. So people online, if you have any questions, doubts or typing. And another interesting thing to do with plot ms is we could also yeah, we could also check our baseline coverage. So this will be x-axis with UV wavelength, which is our baseline in the unit of wavelength, and y-axis will be the amplitude. So here I'm setting field equal to. So if you check the list observed file, you will see that field number 2 is one of the calibrators. I think it's Cirrus in this case. Yeah, I forgot. But anyway, you can set into any field, like even like set to the science target field to check how those observed UV coverage is like. So this is actually a useful plot. For example, here you can see like the maximum baseline is about is in some number, and then you can like use this to infer the beam size or something. And I'm also going to do it myself. So does everyone successfully bring up the image? Okay, awesome. Okay, and then let me bring back the slides. Okay, so now we can start to we can start to do cleaning basically. So you don't have to worry about the remove face cal star command. So this is put in the script just because in case you want to go through all this again, you definitely need to you definitely need to delete any old files before you want to create the file with the same name. So now we are using tclean. So I'm going to go through all this command first, but you can definitely also copy and paste at this point. So right now we are setting field equal 3 to look at the phase calibrator, just because phase calibrator is usually a point source, and I mean, imaging the phase calibrator would be pretty simple. And we are setting nothing to spectral window because this is a continuum image. So we want to use all the spectral window for our image. And then for spectral mode, we are setting multi-frequency synthesis. Again, because we are looking at continuum, so we want to include all frequencies. And we are using Hawk-Bum as a deconvolver. So a simple explanation for Hawk-Bum is that it assumes that each component that tclean finds has a single amplitude across all the frequencies. And because in this case, we have a very limited, less than 10% fractional bandwidth. So this assumption should be okay, and we're using Hawk-Bum. But I know sometimes in band 3 or band 4, the fractional bandwidth could exceed 10%. And in this case, we might want to use the multi-MFS deconvolver. but I'm not going deep into this, so you can always find which to use in detail on the Elman guide on the website. And because we are only imaging a single pointing, we are using just using the standard reader. And for the cell size, so in principle, we want at least 5 cells across the minor axis of our synthesized beam to ensure sufficient sampling. And as I mentioned, you could estimate the beam size by doing plot MS and see the maximum baseline and calculate the beam size in arc seconds. And you also need to set an image size for this. So you don't have to worry too much about this actually, because if your image size you set your setting is not enough to sample your beam, your primary beam, then CASA will pop out a warning saying that, oh, the image size is not sufficient. So you can like try until which point the warning goes out. That means the number you're setting is reasonable. Yeah, so here T-Clean will kindly tell you if your image size is efficient or not. And there is also a weighting, and we could do a couple different kind of weighting algorithms. So weighting is basically you can imagine like the UV coverage we have, like it is usually being more sampled in the central region. And for the extended baseline, it is more sparse. And so if we do a uniform weighting on these UV sample point, it is like you can imagine like for long baseline, the high resolution part, the fidelity would be bad, right? So in this case, we can do some, like for example, for natural weighting, it weights more on the, it basically weighs based on the data points you have for each grid to account for like the non-uniform sampling from our antenna arrays. So here we are using Briggs weighting. So if I remember correctly, this is a intermediate between uniform weighting and the natural. And this is usually a good choice. But depending on your science goal, like depending if you really need the high resolution, then you could use uniform weighting. But if you care about the image fidelity, you could go more toward natural weighting. So there are actually some good YouTube videos that Elma put on their webpage as part of the Elma primer. And if you're interested, you could check out these videos. And then the last comment here is threshold. So now we are setting it 0. So threshold basically is one of the stopping criterion we set for T-Clean. So it will stop when the residuals fall below the threshold. But since we're setting to 0, it's not going to stop if we really set 0. But the thing is, another stopping criteria is number of iterations. So it's n iter. And by default, it is setting to 0. So we're not setting it. So right now, the iteration number is 0. So if we run this command, it actually did not do any cleaning. So go on and try it. It will not do any cleaning, but it will still create the image and PSF. So that it basically gives us the 30 image and 30 beam. Have everyone tried it here? Okay. Yep. Oh, yeah. So with OS 14, I think that interactive, I didn't bring the interactive about.
updated electricity last weekend.
I mean, it wouldn't pop up because we are not doing any cleaning at this stage.
Oh. Now you're.
Yeah, so I just did the same thing with in my CASA, I put the clean command, and remember, because we're setting iteration equals 0, so it actually does not do any cleaning. But if you go back to the directory, you will see it did create some image starting with base cal, which is the image name we set. And so we can use CARDA to look at what these images look like. So it will basically be 30 image at 30. So if we bring up CARDA, so for me, it would be it open on a web browser, and if I open the created image, this is what the 30 image looks like. And we can also see what the 30 is, which would be a PSF. So you can see, like, clearly see, like, these artifacts are definitely like something caused from the PSF instead of real signal. Is everything okay with people online? So those people here see CARDA with the image fine? And, oh, what's happening?
Time's up if we don't do.
But what? Well, what do you mean by like we are not doing?
We have to, every now and then, yeah.
That's so silly.
But we didn't do it. How do we got this back? Let's go.
Sorry, we're having some problem in the projectors here, so we're trying to figure out.
One.
Mm. Okay, yeah, so this is what you should be seeing. This is the dirty image. So since we are not actually doing any cleaning right now, you could remove all those files, just type in remove -rf and face tell dot star. This will delete all the files starting with face tell, because we are going to do real cleaning uh, by naming the image with face count. So be sure you remove this file. Right. Has everyone removed the file here? Okay, awesome. So now to do the real cleaning, we have to set the number of iterations. So here we just set, since we are actually doing interactive cleaning, we can set a random large number and it will pop out the cleaning interface and then we can do cleaning manually. But yeah, so if you cannot do it, I would suggest you set a small number of iteration, like I think 2 is enough. No, like 200 or maybe 500 would be enough to get a decent clean image. But this is based on my experience, of course. Like so for Mac OS 14, I believe the interactive cleaning wouldn't work. Yes. Yes. So you could, for those using Mac 14, you could set interactive equal false and then use CASA to do all the stuff. Oh, okay. Yeah. But it's just that we actually wouldn't really need that many iterations. Yeah. Over clean. Okay, so yeah, so let's do this. Just copy and paste the tclean command with n iter equal 5,000. Oh, yeah. Yeah, I'm running on this script. Yeah. And it takes some time, although it didn't really take me much time when I run at home. Let me figure it out. Oh, I guess it's because I forgot to delete my files. Yeah, I asked everyone to delete, but I didn't do it myself.
The command from the script.
Yeah. Right, now let's do it again. Oh, I think I might remove files in the wrong directory. So I'm going to do it. So, so does the interactive show up for you guys? No? Yeah, it should show up like this.
Now I don't know.
What is it? Oh, okay. So wait, so does this pop up in your laptop?
Yeah.
Okay, great. So what we are going to do is we are going to clean the image. And to do this, we are going to set the mask. So there's a R with a circle here, which allows us to draw an oval around the source, which we believe is true. So I'm just going to draw an oval here, and you can move this. And once it is done, you double click and you will see the mask is set for this region. If you can't do the interact, you can just watch it. Can you do the interact?
No.
No?
The first time we did something well, never have the run. And then I do.
Oh, okay. All right. Yeah, this is, I don't know why I wonder if they will fix this for,
No,
Right,
there was
to-
an issue of not being able to install it, you need that, so. you feel that
Uh-huh.
they have to work with pipeline. Pipeline's supposed to do the same. too.
Oh, yeah, makes sense. Yeah, I think they are actually trying to, replace many of the CASA functions with CARTA. Yeah, so. Yeah, so, but like this interactive cleaning is just, getting you an idea like how cleaning work. So after I set a mask, I can click this green arrow and it will start first round of cleaning. Okay, you can see initially the iterations was about 5,000 and now like it did like a 16 iteration. And so this is actually the residual we're looking. So clearly it is still like not cleaned enough. So we want to do another clean under the same mask. Okay, so now you see that the residual, like the residual contour roughly match the noise level. This means the clean should be okay right now. Of course, like we can continue cleaning. We can see like once it's still like kind of brighter than the noise, but like depending on how deep you want the cleaning is. But at this point, we can stop here and press the red thing here to stop deep clean. Okay. So after we stop deep clean, we will see it create the cleaned image of CSS, and we can load it in CASA, in CARTA to see how it looks. So I'll load in the row in. What is it? I might need to reload CARTA actually. But I think I would bring up the slide first. So yeah, so this is just a procedure of what I did, setting a mask. So first you can see the noise does look a little brighter after we did the first cleaning, and then it looks like much brighter after the second cleaning. Okay. So so we can, so actually, so that was the phase calibrator we are looking at. So if we want to, really we should do cleaning on the science target. And so now we are going to split out the science target data, which is field number 5. And we're going to average over 8 channels to like reduce the data size a little bit. So ignore this remove file thing and run this split command on field number 5 to create a smooth visibility. Yeah, try it. So did the split work for everyone? Like the split command? It's also on the script file. So this will not pop up any window. It is just like splitting our science target field number 5 into an individual smooth visibility file. Yes. So I see a question on chat. You sure how to draw the circle again and run things in the CASA viewer? Couldn't get the green button to run anything. Yes, you should double click. Like after you draw a green circle, you should double click within that circle, and that will set the mask and turn into a white contour around your signal. Yep. Okay. Let's see. Okay, so after we split the field, one thing we have to be careful about is since now we are splitting out the science field and create a new visibility file. Now the field number would actually change to 0. So you can check that with list ops and you'll see that field of the highway is now field number 0. And we actually only have that field in that file. So yeah, so we can do this again, do T-clean again to see how it looks after cleaning our science targets. So does non-interactive T-clean with like iteration of 500 work for you guys? Like, do you got to create the clean images? And are you able to view it on Carta? Like it looks clean? Okay, great. How about Liz? How are things looking? Sure. For the science target? Okay. Okay, two circles again. I'm doing the P-level hydrate image. So again, we want to set a mask with oval, and you could actually zoom in if you think it's too small. And then we would draw a mask around the region where we think there is real signal, and then double click to set them. And then we can run. Yeah. So this is the first clean. It's like 84 iterations. You can also see the noise looks brighter, but still the source is much brighter than the noise, right? Especially this slight lobe here. So we definitely want to clean again. Okay. So now you can see the level of noise of the brightest noise is actually similar to our source. It's like whitish color. So for a shallower clean, this should be fine. We can stop the T-clean here. And then we definitely want to use Carta to look to see how the clean. So the continuum. So this is after cleaning, and we can also bring up the 30 to see how it is different. Oh, we actually didn't have the image because like we didn't do it with a science target, but we can look at the PSS. And yeah, so you can see like most of the artifacts are actually like from the PSF are actually removed from our image. So things are okay, like everyone followed along. Okay, yeah, so this is just a demonstration. After the first 84 iteration is not enough, so we do another iteration, and now the brightest source, the brightest noise have a roughly the same color source. So this is how it looks, okay, so now we have an idea of how to do the cleaning, but there is actually a last step for processing a continuum image, which is the primary beam correction. So you could imagine that for a beam, there is actually attenuation of beam when you go towards outside the beam. So you could we could expect that the noise should be higher near the outskirts of the beam, and also on our primary beam, like on our field of view. That's why, like when we see most of the data, like the noise are higher in the edges. So we should do this correction. So ignore this, remove thing, and do IMPB core, and input the image we clean, and it will output a PD corrected image. And we can see how that is different from before correct. So basically, I think IMPB core just, it's a like simple dividing. It's just like using the continuum image we created and divided by the PSF to account for the attenuation. So that's actually a very simple calculation. And we can use CASA to inspect how it is different. And I see something in the chat. Yes, so I see Peter is already responding. So people are asking, how would we know that the blob at the left top corner was noise, or is that actually real emission? So yeah, so that's why it's important to inspect the point spread function, the dirty beam, so that we have a sense of how, like what the artifacts may look like from the dirty beam. We can, yeah, determine it's a noise or the real signal. Yeah, and this is the first part on continuing imaging. I don't know if people have any questions or problems with following along. Are things all right, Paul, on your side? Awesome.